we had a homework which was to distribute 4 distinguishable oscillators having total energy 4 epsilon among the energy levels which are separated by 1 unit of energy, that is epsilon. So we have the energy levels like first one, that is the ground state having energy 0, the first excited state, here we are assigning it as quantum number 2, it is having energy epsilon, and in this way this is quantum number 3, it has energy 2 epsilon, for 4 it is 3 epsilon, and it approaches in this way. And we are using the pattern that with increase in height energy increases, so we are using the y-axis to be increment in energy like this. We will follow the same pattern, and from now on we will ignore this energy and quantum number to make our diagram simple. So I have described in the previous class that when we were taking 4 indistinguishable particles, then we were getting 5 macrostates. Now those macrostates will remain the same. That is the first macrostate, which is 1111. That is the 4 particles will occupy the first excited state having energy epsilon each. Now in the previous problem they were indistinguishable, but in the present problem they are distinguishable, so we have to arrange them. But internal arrangement within a level is irrelevant, so we are ignoring the internal arrangement. So this macrostate will be assigned with only 1 microstate. So there are no possible arrangement for this macrostate. Now we come to the next macrostate, that is 4000. That is 1 particle, 1 oscillator occupies the energy level, this one, 4 epsilon. Now the total energy of the system is 4 epsilon, so what will happen? The others must remain in the ground state. So the total energy will be 4 epsilon plus 0, 0, 0. Overall, that is total energy will be 4 epsilon. Now here, since the oscillators are distinguishable, we can place A here, in the second case B, third case C, and in the last one D. And when we place A here, we will place BCD in the ground state, here ACD, ABD and ABC. Internal arrangement is ignored, but the positions will change because they are not indistinguishable anymore in this problem. So the number of microstates obtained for this macrostate is 4. We have 4 microstates. Let us now switch to the next macrostate, that is 2200. Means 2 particles, that is oscillators here, are occupying the second excited state, that is having energy 2 epsilon. So it will be 2 epsilon plus 2 epsilon equal to 4 epsilon total energy, and the remaining 2 must be in the ground state to make the total energy 4 epsilon. Hence it is 2200. The coding comes in this sense. Now to have this, you have to first write A, and you place B, C, D. Now for AB you will be left with CD here, for AC it will be BD, for AD it will be BC. Now the combinations for A is obtained. Next we will switch to B. So we write here BC and BD. But we will not write BA because it has been considered here and the internal arrangement is ignored since it is irrelevant. So when we place BC here, it will be AD, and BD here, it will be AC. Left microstate is, here we will put CD, so in the ground state we will have AB. So the number of microstates in this macrostate will be 6. In the first problem, if you remember, I have solved a similar problem. We have 4 balls and 2 boxes. The 4 balls were distinguishable and we got 6 possible arrangements. So this macrostate is actually example 1. Now macrostate 4, it is characterized by 3100. Means we have an oscillator in the 4th energy level and another in the first excited state and the remaining 2 in the ground state. So the total energy will be 3 epsilon plus 0, so the total energy will be 4 epsilon. We have to maintain it because it is the restriction given in the problem. 4 distinguishable oscillators are carrying the total energy 4 epsilon. This is our criteria for solving the problem. When we get arrangement having a large distribution, a wide distribution of particles over the levels, then it will be difficult to find out the number of microstates. So I am giving you a trick, a possible trick with which you will be able to find the microstates. It will be a hectic one, but it will be possible for you to find the number of microstates. Now since you have for A, you have 3 arrangements for the remaining 3, that is B, C, D. So you write here A, and then you write B, C, D here, since there are 4 distinguishable particles. So you get 3 microstates. Now for AB it will be CD, for AC it will be BD, this is simple. For AD it will be BC. Now we change this position by B. So you have to write 3B. Here 1B, the next B and the next B. And for 3 B's, we will have A, C and D. Again, for BA it will be CD, for BC it will be AD, for BD it will be AC. Now you are left with C. So you write 3 C's, C, C and C. So you have to write A, B and D here. Now the ground state is simple. For CA it will be BD, here it will be AD, here it will be AB. And the last one DDD. So you have ABC here. And the ground states are easy, BC, AC and AB. So you get 12 number of microstates for this macrostate 3100. This one is having energy 2 epsilon. And these two 1 epsilon, so it will be 4 epsilon, it is having energy 0. So total energy is 4 epsilon here, so criteria is being fulfilled. Now this macrostate 5, it will also be associated with large number of microstates since the particles are distributed over a large number of levels. So for AAA we write here BCD and this one is easy. For AB it will be CD, it will be BD for AC and for AD it will be BC. Now in the next step or the next set of microstates we will replace this AAA by BBB. Now we place ACD here. Because if we take B, we are left with ACD. And in the third set, we will write here CCC. In the fourth set, we will write D, D, D. And here we will write A, C, D. Here we will write A, B, D excluding C. And here we will write A, B, C excluding D. Now this state will be easy. For AD it will be BC, for BD it will be AC, for CD it will be AB, in this way. Now you will find that no two microstates are similar, all are different, and you cannot generate any other microstate which is different from this set as described in this figure. So we get here 12 microstates. So in total, what we get? For the first macrostate we get 1 microstate, for the second we get 4, for the third we get 6, and for the last two we get 12 and 12. So it is 35 in total. So we have 5 complexants or macrostates, and the total number of microstates for this system is 35. Now each microstate is equally probable. The probability of getting this microstate is exactly equal to the probability of getting this microstate. And also it is relevant and true for microstate corresponding to any other macrostate. All microstates among these 35 are all equally probable, but the most probable distribution is with having the maximum number of microstates. So this macrostate 5 is more probable since it is having the large number of microstates. Macrostate 4 is also more probable corresponding to relative to macrostate 1, 2 and 3 since it is having the large number of microstates. But here this microstate and this microstate will have the same probability, but the most probable distribution is this macrostate since it is manifesting large number of microstates. Now for microstate 1, what is happening? It is having only one microstate, so it is the least probable. Macrostate 1 has the least probability and macrostate 4 and 5 has the highest probability, and the probability increases from 1 to 2 to 3 to 4 to 5 in this way. Now we will try to find out an interesting thing. You can easily observe that how much hectic it is to find out the number of microstates. So for a system with n number of particles in total, here it is for example 4, and n1 to be the number of particles in the first quantum level, n2 be the number of particles in the second quantum level, and so on. So in total we have n number of particles in the entire system, and each level is being occupied by n1, the next level n2, next level n3 and so on. So it is representing a macrostate obviously, because in one macrostate we have a certain number of particles in one level, a different number of particles in another level, and the entire set changes when we switch from one macrostate to another macrostate. So for a macrostate, we can find the number of microstates bypassing such hectic paperwork. So number of microstates in a macrostate is given by the combination n factorial by n1 factorial, n2 factorial, dot, 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 dot. And it is represented by the sign omega, and it is termed as the thermodynamic probability. Very important term. It is symbolized as omega and is defined as the number of microstates possible for a macrostate, and calculated by this expression, that is n factorial, where n is the total number of particles in the system and n1, n2, n3, dot, 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 and so on are the number of particles present in the levels in that macrostate. Now let us check that whether this formula works or not. So we have here first one. This one is macrostate 1. So omega must be equal to 1 since this is the number of microstates for this macrostate. Now using the formula we will have, this will be 4 factorial because in total we have 4 particles, and number of particles in the first level, it is 0, so it will be 0 factorial. 4 particles are present in this level, so it will be 4 factorial, then 0 factorial, and so on. So this 4 factorial and 4 factorial will cancel out and it will give us 1. So it is matching. Now for macrostate 2, this is omega equals to 4 factorial by, we have 3 particles in the ground state, so it will be 3 factorial, then 0 factorial, 0 factorial, 0 factorial, and in this step we have 1 particle, so it is 1 particle, then dot, dot, dot. So it will be 4 into 3 factorial by 3 factorial, and these all will be 1. So 3 factorial will cancel out, it will give us 4. So number of microstates is 4. If we try to calculate what will be the result, it will be 4 factorial by 2 factorial, 2 factorial. So 4 into 3 into 2 factorial, 1 will cancel out. It will be 4 into 3 equals to 12, 12 by 2 equal to 6. You see the number of microstates equal to 6. So it is matching. Now for this problem, this macrostate 4, what will happen? Omega, that is number of microstates, equal to 4 factorial by, we have 2 particles here, so it is 2 factorial, then 1 factorial, then 0 factorial, then 1 factorial. So it will be 4 into 3 into 2 factorial by 2 factorial. It will cancel out, we will get 4 into 3 equals to 12 microstates. So it is matching. Now for this problem, macrostate 5, we have 2, 1, 1, 0. So let us try to find out the number of microstates, that is the thermodynamic probability. It will be 4 factorial by, it is 1 factorial, 2 factorial, and 1 factorial. So 1 factorial, 2 factorial, and 1 factorial. So it will be 4 into 3 into 2 factorial by 2 factorial. It will cancel out, so it will be 12. So it will have also 12 number of microstates. So this formula, this quantitative formulation is predicting the number of microstates for a given macrostate, and it is termed as the thermodynamic probability. We have the following states, the quantum levels. Here we have energy equal to 0. The first excited state, here we have energy epsilon. Now the average population in any quantum level is obtained by summing up the total number of particles in that level, considering all possible arrangements and dividing the sum by total number of distributions. Now if we want to have the average population in the ground state, then we have to count the number of particles present in the ground state in all possible arrangements. Here we have 0, so we write here 0. Then in the next, here we have 3 particles, 3, 3, 3. So 4 into 3 equals to 12. 12 number of particles in the ground state. Next, macrostate 3, we have 2 particles in the ground state and there are 6 microstates. So it will be 6 into 2 equals to 12. Then comes macrostate 4. Here we have 2 and 12 microstates, so it will be 24. And in the 5th macrostate, we have 1 particle in the ground state and 12 microstates here, so it will be 12. So in total, we have in a similar way, if we try to find out the number of particles in the level 2, that is the first excited state, then here we will get 4. So we write here 4. Then here we have none, so it will be 0. Here we have none, so it will be 0 again. Here we have 1 and there are 12, so it will be 12. And in the last macrostate, we have 2 here. In each there are 12 microstates, so it will be 24. So it will be 40. Now in this way, if we try to have the remaining ones, we will get. Now I have already told you that average population in any quantum level is obtained by summing up all the number of particles in that level considering all arrangements and dividing the sum by the total number of distributions. So the average population will be given by, here we will divide, this is the average population, it will be P1 equals to 60 by 35. 35 number of distributions are available. It gives us 1.714. For the second level, it will be 40 upon 35. It is giving us 1.42. P3, it is 24 upon 35, so it will be 0.685. P4, 12 by 35, it is 0.342. P5, it will be 0.114 by dividing 4 by 35. So we see that the average population for the ground state is 1.714, for the first excited state is 1.42, and for the next level is 0.685, higher level 0.342, next higher level 0.114. Now in this direction, what is happening? Energy is increasing and we see the population is decreasing. So we can conclude here, this is an important conclusion, that with increase in quantum level population decreases. Another conclusion can be drawn, that is, let us consider a system A. Say it is having one particle having energy 3 epsilon. And let us consider another system B. It is having 3 particles and having energy epsilon only. So in total it will be 4 particles and having energy 4 epsilon. If I brought these two systems, if I bring these two systems in contact. So let us do this. We bring these two systems in contact and isolate the combined system from the surrounding. What will happen? You can judge that one particle is having such energy, it means that it is at a higher temperature. And 3 particles are having lower energy, so it is having a lower temperature. So system A is carrying greater temperature than system B. It is a cold body, it is a hot body. You have to prove using these analyses, this thermodynamic probability, number of macrostates, number of microstates, possible distribution. You have to predict that heat flows from hot body to cold body. So you have to take this combined system, and in this combined system you have 4 particles having total energy 4 epsilon. So that is the system we have considered in today's lecture. So the combined system is ready for you. Now these systems have to be analyzed separately, and then you have to prove that from this body heat flows to this body. Now don't think abruptly that you have to prove that heat is coming out and it is entering here. You will not get those ideas because we are dealing with statistics here. No heat is involved. You have to predict the flow of heat in this direction just by using the term omega, statistical term, which is the thermodynamic probability here, omega. So you have to prove that in the combined system, this state, the particle enjoying the states, is decreasing. The probability is decreasing, and you have to prove that the thermodynamic probability of this particle to enjoy lower levels compared to 3 epsilon is increasing, and the probability of enjoying higher levels compared to 3 epsilon is decreasing. So this will prove that it will lose energy, and that will be transferred to this one. So this system is ready. Today's lecture, you have 35 microstates, and this system you have to make it ready. And from the analysis you have to predict that the probability is decreasing. Probability of what? Probability of enjoying energy greater than 3 epsilon is becoming much less, and probability of having energy less than 3 epsilon is increasing. So that means it will lose energy and this will gain energy. So this is your next homework. Submit it in the comment section, and then I will switch to an important problem, that is thermodynamic probability and entropy. We will discuss this homework in the next lecture and we will continue with the topic thermodynamic probability and entropy.